But you know, a lot of the time you're in the position of you're in charge.
All right, any questions? Okay. Holding on this for some reason. See, if I recall correctly, we have just basically started on rotational motion and we just got through definitions, in essence. Or at least being able to transliterate equations. Am I correct on that?
I believe so.
Okay. Patrick, you look concerned.
I'm not.
Okay.
What do you mean by transliterating?
The fact that you can take any of the equations, like take the cake formula. And get rid of the crappy marker. And this is the one of the cake formulas for linear motion, but we can just transliterate as in, instead of x, we use theta. Instead of v, this equals omega it plus 1/2 alpha t squared, where we just put in the rotational analogs. So the change in the angle is equal to the angular velocity times time plus 1/2 angular acceleration times squared. That's what I mean by transliterating.
Right.
All right, so let's, other questions? So let's take a look at kinetic energy. And what's the formula?
1/2 mv squared.
Two of you were in unison. You might have been doing ventriloquism, which would be also impressive.
You want me to do while I drink water?
All right, so we know the formula for kinetic energy, but if I take an object like this, so I have an axis of rotation here, and this is swinging around it. Well, I have a mass at the door, that's not a problem, but what about speed? What do I use for speed of something where not everything is traveling at the same speed?
Angular speed?
Yeah, but I just can't pop in an omega in for v. I have to justify it somehow. If we were doing an approximation, what would you choose for v?
Arc length? Or
You
What do you mean by arc length?
the distance traveled by the end of it?
Except v is a speed.
I mean the linear velocity at the end?
Okay, so you would pick, to do a rough estimate, you would take the speed at this point right here? Is that what you're saying?
If we're going for a rough estimate, we would go for the speed of the center.
Okay, so speed of center. This probably makes more sense than that does, since this is the fastest part on here. It would give you an upper bound, that's for sure. So we can do a very crude approximation of 1/2 the mass of the door times the speed of the center squared. But it is a very crude approximation. We can get a slightly better approximation if we, instead of treating it like one object, treat it like two objects. We got an upper half and a lower half, and we'll just take an average of that. So we got a better approximation by 1/2 m, I'll just call it m sub 1, v sub 1 squared plus 1/2 m sub 2, v sub 2 squared. Obviously, how would we get a better approximation?
Continue splitting it.
Say it again?
Just continue splitting the door into multiple
Yeah.
masses.
So the more parts I break it up into, the better I'm gonna be. So let's go ahead and sort of work that out. So it's just gonna be the sum of all the individual parts, so let I go from 1 to begin. 1/2 mass of whatever that mass is of that part times the speed of that part squared. Now, obviously, 1/2 is a constant, I can just pull that out. We can't assume that the mass is constant. If we break it up into even pieces at least, the m would be a constant if we knew what n was, if the density was uniform. And we don't know that for sure. So we got 1/2 mvi squared, but the 1/2 is a constant, so it can factor out. Now, obviously, this is so much simpler than, all right, so let's actually get it to where we can simplify it. Let's bring in something that Patrick had mentioned, angular, well, he said velocity, but angular speed. What's the relationship between linear speed and angular speed?
Linear,
No,
linear speed is equal to, it's angular speed divided by radius multiplied by, I forget.
the radius squared.
Multiply times radius squared,
No,
divide by radius squared.
is the. Never mind.
Let's think about units. What are the units of speed?
Meters per second.
All right, units of angular speed.
Radians per second.
So obviously, we need to do something to get meters to radians. In a circle, what's the relationship to, what's a radian?
The length of the radius.
Okay. At least that would be the arc length. So times meters per radians would work, and in essence, it's V is equal to omega R. Is there a different equation you were thinking of, Mike?
No, I just mixed up, dividing by R versus multiplying by R.
Okay.
Is it the centripetal acceleration that's divided by r squared?
That's V squared over R.
Oh,
The only equation I think we've dealt with so far where you divide by R squared is the gravitational force formula.
makes sense.
All right, so we have this relationship here, and this is a rigid body, and we are making that assumption, even though I had not stated that, so rigid body. And what I mean by rigid body, wow, that is just absolutely hideous. Is that all parts of it will rotate together. It's not like the top will move. It's not going to warp. That's what I'm getting towards. So if it's a rigid body, they are all rotating with the same angular speed around the central axis. So I'm going to take this, and instead of V, I'm going to put in my omega R, which actually does make life a little bit simpler. So my kinetic energy, 1/2 m sub I times omega omega r sub I squared. Now omega doesn't have a subscript because again, rigid body, all the angular speeds are the same. In essence, omega squared is a constant for this object, and so it can factor out. So I'm left with 1/2 omega squared times the sum of m sub I r sub I squared. Which seems simple enough. At this point, this, if we break it up into an infinite number of terms, well, if I have any mass and I break it up into an infinite number of pieces, this mass becomes incredibly tiny. And what do we call that in calculus? Or I guess, what do you call it in calculus? Have you got it?
Differential?
Pardon?
Is it a differential?
It is. So this right here, if we actually went into an infinite number of infinitesimally small things, it's just the integral of r squared dm. And that is the moment of inertia. If you get into probably mechanical engineering, you'll discover there's more than one moment of inertia. This is the one in physics at this point. This is what we call moment of inertia. Later on, you'll get into moment of inertia of the second order with respect to the mass, or there's a lot of other variations. All right, questions to hear?
What was the definition of moment again?
Moment is a term that shows up whenever you're dealing with rotation.
Okay.
They call it rotational inertia. They did. 348. There. There we go. That's what it's looking for. All right. Now, if you haven't had physics before, you might look at this and go, really, does that help us at all? If you have had it before, at least the rotational piece, you might have some clue or remember that this does help us. This is dependent upon the density and the shape. Now, we will be dealing with a lot of uniform densities, so that makes life easier. But this has actually been calculated already for a great number of shapes. So for example, let's just do that for a disk or a cylinder, however you want to do it. Rotating about its center. Excuse me, just in case. Hello? Yes. All right, excellent. Okay. Okay, thank you. Sure, bye. that's pretty much right. The guy's gonna be there in 15 minutes. Okay. Sorry. Yes, it is. Dave is the guy. There. Bye. Anyway, now that we've had a break. All right, so let's find the moment of inertia of a disk rotating about its normal central axis, as opposed to, and you really need to specify where the axis of rotation is, because if I've got a disk or a cylinder, whichever one, rotating about that axis, I've got a different, it's different. Or like that, rotating around, it's still different. So, I remember going through something like this my first year here, bringing in triple integral. And when I was done, one of the calculus students said, "What did you just do?" I gather triple integrals is not something that everyone has seen before.
I just finished Calc 3, so I saw them.
Okay.
Same year.
All right, so fond memories. Yeah, I'm not going to do a triple integral, but I just, the memory comes back every time. So what I'm going to do is, sort of from an overhead point of view, I got my axis right there, and I'm going to take some infinitesimally small bit of mass, some distance r away. So my moment of inertia, integral r squared dm. Now, I've got r and I've got m, and I need to figure out what I need to get them in terms of a single variable. Well, I know that every point along here, and assume that these are concentric circles, every point along here is the same distance r away. And if I'm looking at that, so I've got some thickness t here, the volume of this, well, I've got a thickness here of dr, because it's in the radial direction, and that's supposed to be an arrow there. So I know that my volume of this basically annular cylinder, of this section that I'm pulling out, well, if I imagine that it's a band and I open it up, it's a rectangle. The thickness is t, so I'm taking that and unrolling it. This distance, so that's the thickness t. This distance right here is the circumference. So 2 by r. And then the thickness this way, dr. I also have this issue of, great, that's dv, but I still need to get to dm. Well, what relationship do I have that relates mass and volume?
Density.
So I know density is mass divided by volume. If it is uniform, that density is going to be equal to, well, that ratio no matter what size I pick. So dm over dv. So dm is equal to rho dv. So my moment of inertia is equal to the integral of r squared dm, which is the integral of r squared rho d volume, which is the integral of r squared rho times t 2 pi r dr. All I've done is just substituting in. So that's my differential of my volume. That is just my differential of my mass. Let's pull the constants out and combine like terms. So we've got rho T 2 pi r cubed dr. I now have it in terms of a single variable, so now the limits of integration. What is the smallest and largest values of r? I guess properly, what are the largest and smallest?
From 0 all the way up to R.
Yeah, then let's go ahead and define the entire radius is big R. So from 0 to big R. And what's the integral of r cubed to dr?
R to the 4th over 4.
So I'm left with rho T pi from 0 to big R over 2 times big R to the 4th minus 0 to the 4th. But wait, there's more. This requires us knowing the density and the thickness, but frankly, the thickness is irrelevant. But let's go ahead and show that why that's true. I know that the density is uniform because I said it was. So that's equal to the total mass divided by the total volume. Times T pi over 2 big R to the 4th. The mass of the whole thing we'll just let be big M. The volume, well, it's a cylinder, so it's the volume of one of the circles times the thickness. So that is pi big R squared times the thickness times T